So, hello everyone. Hope you're hearing me well. Today we're going to talk about hash tables and sets. More specifically about dictionaries and stuff like that. Actually, dictionaries was over here. I didn't circle it right. Okay. Pretty awesome stuff. You can do a lot of things with that. You can even program part of Facebook with dictionaries. You know, the part which translates into your own language, not everything else. So it's pretty awesome stuff, and it's not very complicated. It's basically it's light material. I mean, not programming one, but using them, because we'll talk mainly about how we use them. So let's get it going. What we're going to talk about, dictionaries and hash tables. These two things are basically the same. Well, not exactly. You have a data type in C# for both of them, and we'll mainly use dictionaries because hash tables have some defects and they're not that good for use. But actually each dictionary is implemented through a hash table, and you'll learn how that is done. So we'll talk specifically about the dictionary class and how to use it and what to use it for. And I'll open the door. So, after that short break, more than that, we're going to talk about sets, and that's basically the material we're going to cover for today. We could give you some neat examples. We'll see how the time goes. Okay, so what are dictionaries? You've all seen this kind of dictionary. You've all probably seen other types of dictionaries. You've probably seen dictionaries in C#, but only a little. We'll talk about them more today. Basically, what's a dictionary? Up until now, all of the data types we've used we get their values by giving them some kind of information. For example, we have an array, and we want to get some of the values from the array, and we need to tell that array or list or something like that which position we need. So in dictionaries, well, you know, you can get things in an array, but then you can't give them names. Dictionaries are created with the idea that you should have a data type which can name stuff and get that stuff through its name. So these names we'll call keys, and the stuff that's addressed through these names we'll call values. So dictionaries basically are some sort of collection of key-value pairs. Okay, so what I told you already. Other ways to name it: a map or an associative array. There are a lot of these in JavaScript, for example, if anyone's written in JavaScript. And what it contains: key-value pairs. It contains some sort of structure which has a name and a value. So you can basically search for some values through their name. For example, we can have values like names of people, we can have keys like names of people, and values, for example, their ages or more information about them. Doesn't matter exactly what. Okay, so what a dictionary is meant to do? Well, it should have some basic functions like all other data types. All other data types have the ability to add elements and to remove elements. Dictionaries can do that also. The cool thing they can do is find something by a key. And the whole idea behind this is searching in a dictionary by key is very fast. It's faster than going through an entire array and looking for the element which has this name, for example. Okay, so there are several ways to implement dictionaries. Of course, the most simple is using a list or an array. And how do you implement a dictionary with a list or array? Well, you just make an array, or list, of course, of key-value pairs. And you go through the entire array and check if the key you're looking for is equal to the current key-value pair dot key, then you take the value, for example. That's searching by key. That's a simple way of searching by key. So, or more likely, stupid way, searching by key. You have an array, some sort of array, and you have some stuff inside. And what this stuff consists of? Well, it has a key and a value. When you're searching for something specific, you go through the entire array, look through it, and when you meet a key that corresponds to the key you're searching for, you print the value, for example. So, that of course is slow. You could do it. You will use up exactly enough RAM for your elements, but searching in it is slow. So, that's why we have the abstract data type hashtable and the abstract data type balance tree. Both of these are used in implementations of dictionaries in C# and other languages, and we'll see how. So this is some example of a dictionary. This thing over here is a key, and this key can be anything, not only strings. It could be an object, it could be an integer, it could be whatever. It could be the class myPerson. So we have some keys. For example, these are strings in here, string keys, and some string values. Values again can be integers, pointers, or whatever you want them to be. So that's a dictionary. That's how a dictionary looks, basically. That's the concept. And how do we implement them? Well, we implement dictionaries with using hash tables. Okay, what's hash table? It's not a cache table. Some of us wish it were, but whoa. So we just got screwed. So we were talking about what is a hash table and that it isn't a cache table. So a hash table is something that maps values to some keys, basically the same like the dictionary, but it uses some kind of function, some method, some algorithm which takes a key of any type and transforms it into a unique number. And that unique number is a unique position, or almost unique position, in some array, and that hash table places our value at exactly that position. Meaning, what we have is a hash table. We have an array. In this array, we have key value pairs. This thing is a key value pair, this thing, all of these things are key value pairs. So, how do we decide where to put one key value pair? We have the key, so we have, for each key value pair, we have, of course, the key and the value. Okay, how do we decide on the position? Well, we use a thing called a hashing function, or we hash. The process is called hashing. And what does hashing mean? Well, basically, take some information and transform it, calculate some algorithms, and transform it into an index, the index of some position. And then, of course, put the key value pair in there. Okay, so basically, you doing a hashing on some object gives you a number, and that number should be in the range of the number of values you have in your hash table. Okay, so this hash table, for example, has size m. That's the total capacity of that hash table. And of course, it finishes with the m-1th symbol. Not symbol, but element. This is the hash function, and the hash function, not only that it gives us a number, it gives us a number in exactly this range. So between 0, the first index, and m-1, the last index. So, you've probably gotten the idea. Moving on. So, yeah, basically this was a hash table with m slots, meaning that the last element will have index m-1. And this hashing function, as I already told you, takes some information and transforms it into an index. So, doing a hashing function on the key k gives us a number in this range, which I already said. Okay. We could also have collisions, meaning that a hash function on two different keys gives us the same value, but we'll speak about this a little later on. So, the idea is that for each and every key which we give our hashing function, it must return that index in that range, in this range. Not lower, not higher. So, basically, if a hash table can't do that, if a hashing function can't do that, we need to resize our hash table, meaning we need to have more positions. Okay. So, what's a perfect hashing function? There's a bit of terminology in this lecture, but you get used to it. So, a perfect hashing function is a function which is, the term I think was injective or bijective, whatever. That doesn't matter much. What it means is a perfect hashing function can map each and every key, which we can give it. If we have a multitude of keys, for example, we have this set of keys, we have some key, another key, etc., 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 a lot of other keys. Each and every one of these keys has to be uniquely transformed into another set of new keys, of hashed keys. For example, here we have hashed key 1, hashed key 2, etc., etc., etc. But none of these overlap. That's what a perfect hashing function does. If we call this thing perfect out of k, and this is k over here, each and every element of this, for example, is h. Each and every element of h can be transformed backwards into an element of k. So that means that you can't have two keys which, when hashed, give the same result, give the same position. That's what a perfect hashing function does. Implementation of a perfect hashing function is hard, if not impossible. It really depends on what keys you're using, what's the set of those keys, and how fast you want your hashing function to be, and how much memory you want to use. So basically, making something like this, a perfect hashing function, is something considered almost impossible, which arises problems. Meaning that if we can't make a perfect hashing function, we'll have some collisions. What a collision means is you have two different keys that map to the same position. So then you have to resolve somehow that collision effect. So what we generally use, what in programming is generally used, is using an almost perfect hash function. What an almost perfect hash function means? Well, it means that collisions are as rare as possible. It means that when you have a multitude of keys, there could be two keys, for example, key 1 and key 2. There could be two keys which map to the same value. And that value is, for example, h1. Mapping to the same value. But this thing should be very, very rare. As rare as possible. But it happens. And how do we resolve stuff like that? We'll see a little bit later on. So what you could have, as we said, a hashing function transforms the key into a position. So if you accidentally happen to have two keys, key 1 and key 2, which map to the same position, what do you do with the value? So we have both of these using the hashing function mapped to this position. This is the position, for example, 5 or something like that. Then we have one position and two key value pairs to put in there. Well, we'll see how we deal with that in a moment. So collision, that's what I showed you. Two keys with the same hashing function give the same position. That's collision. That's what we don't want to happen, because when that happens, you have to work around in some way. So when that number of collisions which you could reach, meaning that if there are, for example, 10 out of 1,000 keys where you can have a collision, meaning that all 10 of them, for example, map to the same position, then it's basically okay. That's a not so perfect hashing function, but it works. So, again, using a hashing function that makes no collisions is almost impossible, creating that type of hashing function. So, what do we do when we reach that situation? Well, the most commonly used method is we have some array, and we have two keys that map to the same position. So this is the same position. What do we do? Well, instead of keeping just key value pairs, we keep a list of key value pairs. So each position is actually a linked list, for example. So this linked list points to some elements, and these elements are all the collisions, meaning that if we have two key value pairs which map to the same position, what do? Well, we make a list which holds the first one. So this is the first key value pair, K1, and its value, V1 for example. And this is connected to the next element, K2 and V2, meaning that the second value and the second key and the second value. And what do? Well, when you have a collision, when you know that at this position you have more than one thing, what do? Well, you know the key you're looking for, so you just search through these elements. You reach this position, you do the hashing function on the key you're looking for, you go to this position and start searching. Okay, we have two keys. Well, which one of them matches the one I'm looking for? For example, I'm looking for K2. So what do? Well, I do the hashing function. I get the position where these two are located. I get this position. And I start searching through this list. I go to this position and see, is K1 equal to K2? Well, for example, it isn't. So then we go to the next position and check again. Is K2 equal to K2? Well, it is. And we get the value. That's finding when we have a collision. There are other ways. Generally, in a hash table, you have positions around your values. For example, you have a value here, you have one here, etc., etc., etc. Some can be closer to each other, but you generally have free space in a hash table, meaning that around one value you will have empty cells, nothing in them. So what do when you have a collision? Well, first member goes in here, the second thing that maps to this place doesn't go here, but it goes to the next cell, for example. That's one option to avoid collisions without using lists. The other option is rehashing, meaning that you get a hash code for some number, or string or whatever. You get that hash code, and you see that that position is already taken. And what do? Well, you do the hash code on the number again. You do the hashing algorithm on the number again, and you do it again and again and again until you reach some position which doesn't have any anything in it, any full cells. Meaning that if you have, for example, a hashing function that maps to the 41st position. This is 41st, and this is 0, and this is m-1. And you see that this position is full. Well, you do the hashing function, but this time not on, for example, ABC. For example, you did a hashing function on ABC, and it mapped to this position over here. And you see that this position is full. What do? Well, you do the hashing function again, but not on ABC, but on 41. And you get something different, for example. Again, this is not a very reliable method. There are optimizations for it, but what you mostly use is just chaining in a list. Meaning, when you get two same keys, two same hash results, you just make a list and put them into that list at that position. Okay, so here's an example of a collision. We have some strings. Our keys are strings, and these are the strings, and this is the hashing function, which does and transforms. Here you see what it does. It transforms, for example, Peshu into 4, and 4 is a position in our array. And what happens when we have collisions? Well, first of all, what happens when we don't have collisions? In each of these places we have lists. Where we haven't filled anything, we have no. So this is no, because none of these map to 0. All of these are some numbers different than 0. None of these map to 0, and then you have no. At the first position, what happens? Well, we have one person, one key that maps to the first position, and here's our key, Mimi, and it has some value, for example. And then we have no. Why do we have no? Well, because our list is no terminated. We studied what a linked list means. This is what a linked list means. Some elements ending with no at the end. Okay, so position 2. At position 2 we have a collision. We have Kiro and Ivan mapping to position 2. Both of these go to 2. What do? Well, we put them in a list again. And we chain them one after another. The first one that got mapped is Kiro, so he goes here. And after that we have no. Then we said Ivan goes at the same place. Then what are we going to do? Well, Kiro is no longer followed by no. It is now followed by Ivan. And this thing reroutes itself to Ivan. And Ivan then goes to no. And if we have another person who goes to the second position, he will come after Ivan, etc., etc., etc. That's how we resolve collisions using a list. And that, I think, is the most commonly used method. Okay. Mainly because it's fast and it's not so memory wasting. Okay, so that's chaining. Okay. Hash tables, considering what we want to do, meaning getting an element by its key as fast as possible, hash tables are the best implementation for that abstract data type for the dictionary. Finding, deleting, and etc. they take always constant time. So basically, if we have 1 million elements, if we have 20 million elements, if we have 400 million elements, it's all the same. It's always a constant time. And that constant time is depending on the hash function. It depends on how fast our hash function is. It could depend on the length of the key. But that's in rare cases, if we have strings, for example. Mostly, these things will work in constant time, or at worst at time dependent on the key. But keys will definitely be shorter than 400 million symbols, for example. Or at least most of the time. So, what this thing is good for? Well, when you need something to happen fast, searching for something fast, when you know its name, you use a hash table or a dictionary which implements that hash table. So, for example, my first example, searching through an entire array in which you have the keys and the values, is slow. You know, on average, in the best case, the element is at first position, but in the worst case, the element is, for example, at the 1 millionth position. What do you do then? Well, traverse 1 million elements until you find it. Okay. What you do with a dictionary, you just calculate the hashing function on the key, and you get the index of where that number is placed in your hash table. And you just take that out. So, in the worst case, hash tables are faster, always faster, than just an array. Well, unless the array has 3 elements in it. Okay, what the dictionary interface looks like. You have this thing, dictionary, which is the base of all dictionaries in C#. And how it looks like? Well, it's a generic, and it has a type for a key and another type for a value. So this one is the key, the second one is the value. Meaning that you can put anything in key value. The same way you can put anything in a list, the same way you can put anything in a dictionary. Okay, so what it implements? Well, it's a collection, and it implements IEnumerable. We'll talk about that a little bit later on. The dictionary is what you use most of the time. The other thing you can use is a sorted dictionary. What's a sorted dictionary? Well, a sorted dictionary basically orders its keys, meaning that the first key, for example, alphabetically, will be first, then the second will be second, etc., etc., etc. In the normal dictionary, this thing isn't obligatory. You could have, for example, if we have the keys George, Jason, and Zebra, Zebra could be first in this type of dictionary. But in the other type of dictionary, it will always be last because it's alphabetically the last one. So, that's what you can use. Again, you will most commonly use this one or this one. Because this one is faster than the sorted one, because sorting takes time. Basically, not only that, but the inside implementation of a sorted dictionary is generally slower than the normal dictionary class. So, what hash tables do we have in C#? And this is not the only one. We have basically a data type in C# that is a hash table, literally a hash table. You have this data type, hash table. And what it does, well, it stores keys and objects, meaning that the values are always objects, and you don't have type safety. But don't think of that now. Think of this class dictionary. Dictionary, well, we said what it does. It's basically like a list, meaning that it resizes when it needs to. You don't have to resize it manually, because you don't really know what its hashing function is, or you probably don't know. This thing contains a collection of key-value pairs, as much as it needs. And when it has some collision, meaning that probably it not always maps perfectly. You don't have a perfect caching function. So this thing doesn't map perfectly. But when it has a collision, it resolves it with chaining. As I said, this is probably the most common way of avoiding collisions. Just chaining the elements. Okay. And these elements could have basically random order. They depend on the hashing function. Whatever the hashing function gives for a key, that's what you will receive as an order. If the hashing function puts zebra before George, then you will have zebra before George in your dictionary. As we said, the dictionary looks like an array. And if zebra maps to here, or Z, and G maps to here, those things won't become ordered when you take them out. If you do a for each, you will first get this one, and then get this one, because it will go from 0 to the last element. N minus 1 or M minus 1 or whatever. Okay, so what does dictionary use? Maybe the more important thing. Dictionary uses these two things, equals and get hash code. So, what is get hash code? Well, it gets the hash code of some type of object. For string, for integer, for double, float, short, unsigned short, etc. For all the basic data types. Get hash code is already implemented, which means you don't have to implement it yourself. If you make your own class, for example, person or dog or car, and you want to use it for a key, and I stress on that, a key, not a value. If you want to use it as a key, you have to write your own hashing function. Generally, you should try to avoid that. There's not much use in making your own keys different from integers, strings, or whatever. Why do you need a dictionary which has cars, for example, as hash codes? It's not very... You could use it, but it's in rare cases. What does equals do? Well, it compares keys. Again, if we have some collision, we need to compare keys here. Because we have some list, and this is the first key, and this is the second key, and etc., etc., and so on. And this is the third key. We have to have a way to compare the key we're looking for. For example, we're looking for F. To compare it with K1, K2, K3. Again, strings, integers, and etc. have their own comparing functions. Yes?
Do you have a use spike on your PC?
A what?
Use spike.
What's that?
Something like just the compile.
No. I don't have whatever you said though.
It's abbreviation of intermediate language style.
Uh-huh. So yeah, but I don't have any type of decompiler. What? Yeah, but I don't have it. I haven't installed it on my PC. You could use. All of you can get the a premium collection of tools from Telerik, I guess. So you could probably take it and go through the code if that's what you wanted to do. You probably wanted to see the code, right? I think you have the right to get a license temporarily for Telerik products. I'm not sure.
Just decompile is free. It's free.
Okay, yeah, so just decompile is free. Don't know stuff about my own company. Damn. Okay, so what you wanted to do was basically see the code inside for this thing, or? What?
Many of primitive types
Yes.
hash code.
Yes, most of the primitive types do have hash code, get hash code method. If you create your own one, then you will have to implement get hash code.
Yes, everyone return a different result.
Well, yeah,
Most
they.
implementation is
It's different for the different types. They all
Yes.
inherited from the object class. Get hash code.
The idea is that hash codes are always different. They don't have to be the same for same data types. It's,
I just would like to see.
well, maybe if we get just decompile in the exercises, yeah.
The other thing,
No.
how we are implementing for the object because it doesn't have equals.
Uh,
Equals function.
well, not sure of the implementation at object. You could always implement an equals for anything. You could just check, for example, if it points to the same address. Object is basically a pointer, and it points to some address. So you could check the pointer to the address, for example.
For equals, but not for compiling.
That's why you shouldn't have a dictionary with objects as keys, basically. The idea is that when you have keys, they should be something that is generally unique. Because creating a hash function for something like object, for example, isn't very, very unique. When you the results of the hash function won't be very unique. So yeah, basically what you do is take some kind of key which is generally unique. For example, strings are generally unique. If you make 2 strings, they'll probably be unique.
But not for the arrays.
Not for what?
Arrays.
If you take 2 arrays, if you take 2 arrays for keys, you have to really implement your own hashing function if you want it to be solidly working. Okay, so what you can do with the dictionary, we learned that it has to use objects, some kind of data type, not exactly this one, which should have generally unique properties, as we said, strings, integers, floats even, stuff like that, but not the object type or other stuff. Generally, strings, integers, and floats will be the things which you most widely use, or chars, characters. Okay, so what do we have in the dictionary? Well, of course, the add function. What does the add function take? Add method, more likely. What it takes? Well, it takes keys and values. We say we want to place at the key, for example, Philadelphia. We want to put the postal code some number. That's a key value pair. When you want to add, you add this thing. You add a key, for example, S, and its value, which, for example, is, I don't know, the code of S. I don't know which the code of S is. For example, 112. For example, that's what you want to add in a dictionary. You can't just say add 112, but because it doesn't know where to put it. And you can't just say add S because it doesn't know what to put in the value. You could put an empty value. For example, you could put a null value if your value type can support nulls. Okay, so it has a remove. What does remove take? The key. The same way, in a list you get a remove of an index, for example. Remove the element at that index. Well, in a dictionary you say remove the element at this index, only this isn't called an index, it's called a key. Simple as that. This, when you see this type of construction, it means if you have a dictionary which is called, for example, D, and it's a new dictionary of something. When you say D of, if you have a dictionary of strings and some values, for example, integers, if you have a dictionary of this stuff, you could say D of, for example, ABC. Use this as an index. It's not exactly an index, but you could imagine it as an index. The same way we use arrays and use this thing like an index. Well, the same way you put a key here. If your keys are objects, or if your keys are something else, of course you don't put in strings. You put in whatever your key type is. And you can say this thing equals something. And if this thing doesn't exist, you will get an exception.
What kind of exception? Out of range?
Key not found exception, but I'm not pretty sure. You could check that. But you will get an exception. You won't get index out of bounds because it won't be out of bounds of the hash table. It could be, but it's not likely. Okay. So this, when you see this type of expression, it means your object name, the position at whatever I said here. Okay. So you could do all these operations, get, add, replace. Same way you can use these indexers. This thing is called an indexer. Same way you can use these indexers to manipulate the elements of an array or a list. The same way you can use this indexer in a dictionary to change values, get values, etc. Okay, clear. It does the same thing which it does for all the other collections. It removes all the elements. Count gets you all the elements, not the capacity of the hash table, but all the elements. Keys gets you an array or a list or whatever, some type of collection of keys. All of the keys. So if you don't know what elements you've put in your dictionary, you just say give me the keys, and then go through all the keys and print out the values, for example, or change the values if you want. If you say values, it gives you all the values. Generally, you should more use keys. You shouldn't use give me all the values, but okay, it's an option. It's not that fatal. But here's what's fatal. If you tell it, does this thing contain a value? This thing is very slow. Why is it very slow? Well, because it has to go through all of its things it's written into its memory and check. It's much faster to do this. Contains key, what it does? Well, it does the hashing function on the key, gets a position and checks whether it has something at that position. If it has something, cool, you get an answer true. If it doesn't, you get false. For this, well, it has to traverse everything and see. And if you have two values, yes, it will say it will stop at the first one. If you don't have this value, it will go through the entire hash table and see that there's nothing. So this thing is slow. If you can, avoid it. It's not optimal in no way.
Is there a function which is swapping the key and value?
Swapping the key and the value. Why would?
It will be useful. You need a value, so you're swapping it, searching for key, then swap it again.
You could always get a collection of the keys and check if it contains, if the element you're looking for is at that position at the current key. It's a better idea. You can't swap keys and values because that will be very slow. That means creating a dictionary, a new dictionary, which has reverse types, meaning that the value is the key and the key is the value
Also,
from the other.
You can't swap them because the keys are unique and the values
Yes.
don't have to be unique. So
Well, you can, but you'll get collisions.
yeah.
If the keys should be more or less unique, values could be repeating. For example, you could have 10 people with names George, Lisa, Michelangelo, etc. And all of them will be, for example, living in the second millennium, born in the second millennium. And this means that all of them will have a value too. And if you swap keys and values, you will have all of them put at position 2, or position whatever the hash function of 2 is. What?
It's useful.
If it's useful, you could implement it. We'll study about.
Then you know how much keys have this value.
You could always do. You could always implement your searching. If you want something like that, and you know it's slow, you implement it yourself. If you really want that. It could be, but I'm not really sure if it has a swapping function. We'll learn about extension methods next time. So extension methods is basically implementing something which isn't already built in, and you could implement your swapping of keys and values. it will be possible without writing in the dictionary class. You could write it in your own program and say this is an extension for the dictionary class, and it does a swapping of keys and values. So yeah, next time you'll learn how to do that.
Also, there is sorting only about key, not about value.
Again,
There is a sort for sure. I know.
sorting is a sorted dictionary. Sorting a dictionary means using a sorted dictionary, and it sorts by keys. If you want to sort by values, well, you should probably use an array or something like that. Or you can get all of the keys, get all of the values and sort them. You could
But I want
you could use this.
when I'm sorting the values, I want the keys.
You want what?
I mean, when you are sorting the values, you want to keep the keys. The keys also sorted. According to that value.
Sort keys and values at the same time.
No, sorting just the values, but keep the keys.
The same keys.
Yes.
But they
the-
change their positions in the order.
Yeah, if you're sorting by values,
They will need
you will need to
again.
reorder the keys. You want basically to switch a key from one place to another. Well, if you try to do that, the hashing function won't be correct anymore, because you basically change the place of a key, which that key is calculated through a hashing function, meaning that that key passed through a hashing function and got a number, and you want to change where that number is, and you violate the hashing function. So you can't do that, basically, and you shouldn't be able to do that.
The dictionary has order by and sort methods. Doesn't that actually change the order?
I think there is
Not pretty sure. I think it gives you a collection. The order by. Order by should give you a collection. Should return you a new collection. Or order bys and select and etc. give you new results. And you have sorted dictionary which sorts by keys. And any other behavior would be illegal, basically, because it will violate the hashing function. Okay, so if you're not certain if something has a value, if something has a key, you could say try to get the value of this key, and you will get the value at this out parameter. So you create your object, whatever you have, of that data type, and you get its value through this parameter. You put it in here.
It's the same like the indexing, but just this is
Yes, it's the same like indexing, but this is safe. It won't give you an exception. And why not catch the exception? Well, because exceptions are slow. So this is basically faster than trying to catch the exception. Okay, so how does a dictionary look like and how it's used? Well, you just say, create me a dictionary of keys of strings and values integers. It's called this, and it's a new dictionary of the same thing. And empty constructor means I don't want anything in my dictionary. Then you say, add this thing. You add the key Ivan, and to the key Ivan you add the value 4. Meaning that in our case we have some marks of students, and we have each student and his marks. His one mark in this case. And one mark, etc. So, if you want to, after you add them, get some mark, you just say, give me the mark of Peter. And Peter is a string in this case. And you get some result, which is an integer, which is this over here. And you could write it or do whatever you want. The cool thing, we talked about for each basically 2 months ago. For each can traverse through your dictionary. The dictionary knows which element is next and can give you the next element. So for each can work on dictionaries. What's more specific is that what you get is a key value pair. You don't get the values, you don't get the keys, you get both of them. You get a key value pair. Why? Well, we said that we have this type of thing in our hash table. We have cells. In these cells we have key value pairs. This is a key value pair, this is the key, this is the value. This thing is what you get when you do a for each. So if you want to get the key and the value from that thing, you just say dot key and dot value. Okay, and this is a way in which you can print all of the things in a dictionary, for example. Okay, dictionary with keys and values. Where is my... Yeah, there it is. So, this is a dictionary, the same code which we discussed a little earlier, adding some values, printing some other stuff. Color scheme has been changed. Yeah, thanks much. Okay, so this is Peter in the hash table. This tells us whether we have the key for Peter, and when we see we have the key for Peter, we do some other stuff. Okay, this code is a little different. We remove Peter, we then check whether he is in the hash table again, and then we change the value for students' marks of I1, and then we say that his mark is changed, obviously, and then we go through all of them and print them. Okay, what does this thing do? We'll initiate it. Yeah, hash set and sorted set, that's because I have a different startup project. I always do that. Okay, the dictionary, start that thing again. Peter's mark is 6. Then we started removing him, removed him over here, and our function, which was dot contains key Peter, first was true, then we removed Peter, and then we saw the function again and it got us false. Meaning that if we do this thing, if we say, after we remove Peter, if we say students marks dot Peter dot, not dot, but student marks Peter, I said, Peter equals, for example, we put him a 6, but we already removed Peter, what's going to happen? Well, probably an exception. And we'll start this thing. And, whoa, why didn't it give us a... Yeah, because if you give it a value to some position which doesn't have a key in it, it will generate its position automatically. Yes, we said we have... Whoa. Or not. I'm not really sure what happens here. We said remove Peter, and then student mark Peter is 6. What? It should give us, yeah, it didn't compile the first time. Okay, so things like that could happen. Visual Studio sometimes doesn't compile. So this time what happened? We removed Peter. Somewhere between this and this, we said that we add Peter. We say that Peter has a mark of something. The key for Peter got created, and we got some value in there. And this thing was valid again. And then we used something else.
If we use, for example, not assign 6 value to Peter,
if we try to get students' marks of Peter, control right line of students' marks of Peter, we'll probably get no. Or probably get nothing. If we compile this thing and start it, yeah, you got the key not found. If we try to add, so the setter for this property, this is a property, and what this property does is its setter says, if this thing isn't there, create it. If it is there, just update the value. What does the getter do? Well, it says, get that thing, if it exists. If it doesn't exist, throw an exception, because we don't want to return null. Because if we return null, we'll get problems. Okay, so that's what that indexer does. You shouldn't do that too often. Only if you're sure that these values exist. You should use contains key. It's more safe than trying to catch an exception. If you, for example, want to print this thing, and you've removed it, this could be dangerous. First, it could crash your application. Second, it could slow your application up if you're catching the exception. Okay, so don't use this very often. You could use it, but not very often. Okay, so down from here, what do? We set a value to Ivan. Ivan is over here, and he has 4. We can change it to 3, or to whatever we want. This, as long as it's our data type which we're using. And we can always print all of these guys out, and we just saw them printed out. this thing var says basically key value pair of string and int. Using var means just saving up code. Var is replaced at compile time with this.
Is it safe?
Yeah, because it happens compile time. It's not like object, for example. Var is different from object because object is never calculated what it is. Var is calculated at compile time. And it could say, I don't know what this is, I can't become something. I can't compile here.
Is it considered good code? Or?
Not a very good practice, but if you have a key value pair out of dictionary, out of string, out of list, out of something, it's considered a good practice. But only when it's something long. For example, this thing is long, and it's obvious what it is. Yes?
It could be used for anonymous types because it is used for anonymous types, and this means that you can select some values from an object, and you could create a sub object which only contains the given.
Yeah, as our colleague said, var, what it's used for besides saving up writing code, it's used for when you have, for example, a select or order by or something like that, which gives you a new collection which you're not very certain what it is. You could use var. Actually, that thing creates its own data type, names it with some freaky name which you don't see, and then that thing has some structure. And if you use var on that, it will be a good practice because it's not really guaranteed what that thing is. You're not sure. The compiler knows. You could also find out, but why should you do it when you have a keyword for that? So yeah, basically, as the colleague said, var over here is generally used to either name something that is very long or name something which you're not certain what it is. For example, if you do a select on a collection of some things, select dot order by dot something else, dot find dot etc. Something like link, which we'll use next time. If you do something like that, then use var because you don't know what you get. You get an anonymous type. We'll talk about anonymous types later. So, for now, what you need to know is, generally, when you're going through the objects in a dictionary, yeah, use var. Everyone knows what there is in a dictionary. You don't need to write it every time. When someone looks at your dictionary definition, he knows. So, here, var is okay. But here, for example, here, it's not okay. Saying var here, it's not very okay. It will work, but it's not okay. It knows that, okay, I'm making a var, and it's a new dictionary of something. But if I'm looking at this code, I'll have to see, okay, that's a var, yeah, great. I have to watch what this thing over here is. So that's not a very good practice. Only when you're traversing like this. In for each, it's generally good, because everyone knows what you're doing a for each on. Okay, enough about that. Moving on. How can we count the words in the text? You had a sort of assignment like this in one of your homeworks, I think. You have a multitude of words, you have an entire text, and you need to check how many times each word occurs. First option, each time we meet a word, we search for the word in some array, and we add, for example, 1 to a corresponding position in another array. Bad practice because it's slow. Good one, well, we use a dictionary. Now don't get threatened by this dictionary, etc, etc, etc. This is the base class for a dictionary. Basically what it does is does the same thing that this thing does. You could think of it like this. So whether you write dictionary or dictionary, in this case, when you're just creating a normal dictionary, it doesn't matter which one of them you use. If you're using a sorted dictionary, then it's a little bit different. Okay, so what do? We have some words. For example, using a text reader, you read all the lines from a text and put them in here. Then you split these words into commas, dots, and spaces. And then you see, for each of these words, if it exists in our dictionary, increase the value by 1. If it doesn't exist, well, just say that that position has a value of 1. What we did a little while ago with Peter. Words count, Peter equals 5, for example. This thing does the same. Count is 1. If we have the key, make count equal to the value which we have there plus 1, and then write it into words count at that position. And then go through each and every element of our words count dictionary and print it out in the console.
We could just sign plus.
Yeah, we could just say plus plus here. Don't have this here and say just plus plus here. It's also an option. Okay, so yeah, before balanced trees, I think we have this as a demo. Counting words. This is how to count words. We have some C# text, and we have something written in a normal dictionary, and yeah, we have another sorted dictionary. Okay, so what we're looking for here, make our text, then somewhere split it in the count words method. What does count words do? It has some string array of words, and it says for each of the words in the words, do this, which is, yeah, as the colleague said, this is a little bit too much. We could just say, if this thing exists, words count of the current word at which we're in, yeah, plus plus, else,
I mean, this
words count
working like sign.
What?
Plus plus is working like a sign. If there is no word, then plus plus will add just one value to the empty key.
Meaning that if this thing doesn't exist,
even we don't have to use it.
I'm not pretty sure. Because plus plus on no isn't really defined. We could try this. We could remove, but first let's see it working.
Or then,
but not Peter's mark. We say this thing is a startup project and start it up. And we have these things, but not the sorted dictionary. I'm not looking for this. This is our normal dictionary, and we have welcome is met once, to is met 3 times, are is met 1 time, C# 2 times, etc., etc., etc. Now our colleague suggests that we remove this contains key stuff and remove everything and just say words count of word plus plus, and I think that will create an exception. But let's see. Words count at position word plus plus. Compile this thing, initiate it, and stopped working. Key not found exception. Why does this happen? Because it says get me the value at this position, increase it by 1 and set it.
it cannot get.
And it cannot get the value. So what you do, check if it's there. You don't need this part of the code, it's redundant. Check if it's there. If it's there, plus plus. If it isn't there, make it equal to 1. That's it. Okay, so that's an if-else construction, and that's what it did. It said that welcome is met 1 time, and the other things are met more times. Okay, going back to our presentation, not here. Balanced tree dictionaries. We'll see the sorted tree, but where are we now? 21st slide. Okay, time for a break and for some coffee. So, if anyone has any questions, you can ask them now. You can always ask them later. Yes?
Is there a type or structure or any kind of thing in C# that is sorting like a table? Which is sorting, doesn't matter which key value, which property you're getting, you can sort according to that property, and all the other properties they will keep their.
You mean you want a structure which has several properties?
Doesn't matter how much
and sort by one of them.
Yes.
You don't have anything ready for this, but you could always make a list out of dictionaries which have certain keys and sort by the key which you want to sort. Or have a matrix and sort the matrix by, for example, the 5th column. write your own method for sorting.
Or a
There's-
B3.
What?
Or a B3. You put all the properties you want, and you could write a custom sorting that could
Yes.
sort on any of them.
I was thinking, is there something
No,
which is
I can't think of something which is built in, but you could always implement it if you really want. Because why isn't something like this implemented? Because it's somewhat specific. You could define what you exactly want to do, and when something is specific like that, you just implement it yourself, basically. So yeah, you could Google it, but I think there isn't anything like that. I just can't think of something. Okay, any other questions? Okay, so 10-minute break, and let's go have some coffee. Okay, so balanced trees. Come on. Balanced trees. Balanced trees as dictionaries, more likely. What's that? Well, that's a sorted dictionary. This thing over here. What a sorted dictionary is? We just saw how in our text we had welcome at first position, something else at the next position, etc., etc., etc. And we wanted to. We sometimes want a real dictionary. What a real dictionary is? Well, you've all opened an English dictionary or a German dictionary or something like that. All the keys are ordered, all the words which are translated are ordered alphabetically. Well, that's a sorted dictionary. And the sorted dictionary is implemented through a balanced binary search tree. You don't actually care how it's implemented. You care about how you use it and what you use it for. Well, obviously you use it for a dictionary. For a real type dictionary. If you want a dictionary where things are ordered, you just use a sorted dictionary. Okay, and a sorted dictionary looks the same way. It gets a key and a value type, the same way that a normal dictionary does. And it uses a self-balancing binary search tree. How does it work? Well, when you tell it, give me some key, it has these things or these keys ordered in a binary tree. The same way in which you can order numbers in a binary tree, it orders its keys in a binary tree. And when you tell it, give me the value of the key Peter, it goes through the binary tree and searches for the key Peter. And when it finds the key Peter, it gives you the value associated with that key. Meaning that you have this thing, you have a root, and that root has some key in it. And Peter is somewhere here. This thing says Peter, for example, the string Peter, and has a value associated with it, for example, 6. And the tree is ordered alphabetically by Peter and the other strings. Basically, you have a binary search tree of strings. Not of numbers, but of strings, or of the data type which you're using. And these strings are comparable. You know, you can compare strings, integers, floats, doubles, etc. Yeah, this thing is connected like this, and this thing is connected like this, and this, for example, and this. And here's what you have in one of these nodes. Okay, so everything around here, each of the keys are smaller or equal to that of the root, and each of the keys on the right are larger than the key in the root. For example, if you have integers as keys, if you have a tree like this, for example, you have keys and your values are again integers, and okay, this thing over here is the key, this thing is the key, this thing is the key, and the key is, for example, here is 9, and you have a value 0.3. Don't know what that is. For example, if you want to save all the square roots of some numbers, and you have for 9, this is the key is 9, and the square root is 3. And everything around here will be smaller than or equal to 9, and everything around here will be larger than 9. So, for example, you will have 4, and 4 will, well, not like that. 4, and here you will have 2, and this thing isn't here. 4 and 2, and this thing is like this, and everything here is larger than 4, and everything here is smaller than 4. So, for example, you have here 2, and its value, this is the key, and the value is, for example, 1.44, I think. 1.44, 4, etc. And here you have 8 as a key, and the value of, what's the square root of 8? 2 point something, 2.56. This is what a sorted dictionary looks like in memory, in implementation. It's a binary search tree. It's not a hash table anymore. It's a binary search tree, and you search by key. And that binary search tree is ordered by key. That means that you need to have an implementation of iComparable, meaning that keys can be compared to each other. For example, strings, integers, and something else. Or your class, where your class has a compare to function. Okay, so finding, deleting, and all of the other stuff. As you know, binary search trees work in logarithm of n. Sorted dictionaries are just binary search trees, meaning that they will do everything in logarithm of n. Meaning that for 1,000 elements, you will have 32 operations. Not 32, 10 operations. Okay, so when you need sorted elements, you just use sorted dictionary. When you need a real dictionary. When you don't need elements sorted, you just use the normal dictionary because it's faster. As we said, the normal dictionary has a constant time. This is constant for the normal dictionary. And here we have a logarithm. It's not that it's that slow, but it's still slower. And balancing and issues like that are still computation heavy. Balancing a binary search tree does all these things. That's why it's slow. So when you don't need sorted dictionaries, when you don't need sorted keys, and you will most probably not need sorted keys, just use the normal dictionary. Just use this dictionary. If you really need sorted keys, well, binary search tree. You can implement your own binary search tree even. Okay, so if you happen to need a binary search tree, you could use a sorted dictionary. You could always go the other way around. Okay, so that's about it for the sorted dictionary. What happens how do you add elements? The same way you do with a normal dictionary. Do the exactly same things. Just say, it has the same operation, it has the same methods like contains value, like try, get value, etc., etc., etc. When you traverse it with a for each, the only difference is that you will get the keys ordered. Meaning that you will first get A, and then A, B, C, D, E, F, G, H, I, J, K. And you will get the next thing from these words, which is alphabetically first. And we'll see that with the example of the text we just saw. We have the text, welcome to our C# course, etc., etc., etc. In the normal dictionary, we had welcome first. Why? Well, because the hashing function creates welcome at the first position. I don't know why, it just places it there. Welcome has the lowest key, according to the hash function. Okay, our sorted dictionary thinks something else. Our sorted dictionary is a tree, and will be first. Why? Well, because it begins with an A. And in the tree, and will be over here. This will be and it will have the value of 1. And below it will be other stuff. Okay, so, no, actually it won't be there. And will be, I lied to you, and will be over here. It's the smallest one. This key over here is and. It has the value of 1, and over it are some things larger than and. For example, C# is larger than and it will be here. It is after and. C# key will be here, and its value will be 2. That's basically the idea. Okay, so traversing a sorted dictionary gives you elements ordered. And why do you need that? Well, not pretty sure. You could need that in some cases. If you need it, sorted dictionary. If you need a binary tree, you could hack it and use the sorted dictionary. If you don't want to download third-party libraries. Okay. So basically that's the sorted dictionary. It works in exactly the same way which our normal dictionary works like. There's no need to speak about that more. You just say at the position, not this, yeah, actually this. At the position word, do something. Now, what I told you a few moments ago, yes, you have a question?
Yeah, question about the compare to method. We have to implement iComparable
Yes.
in order to use it, or it's just if we just
You need to implement iComparable.
yes.
You just say this thing in here it's iComparable. Compare to method does this, and you're okay to go. Okay. So, yes.
If you want to implement an algorithm which searches, but it tolerates if a given string is not exactly the same. For example, the first chapter is different, and for example, it returns the first item that is above some percentage, like the thing that we are searching.
In other words, you just want to implement another comparing function for strings.
My question was how good is sorted dictionary structure for a thing like that?
For
your dictionary, for example, you're searching, you're starting with date, then you don't know which is the
No.
I think his question is different.
It's not starting with dates. You have two words, and for example, the first character may be different, but if the rest is the same, then it's almost correct, and you should get this one.
Well, the only difference actually you're making is in the way you compare them, and that means that sorted dictionaries is about good at that as any other structure which does log-n operations to sort or do anything like that. So it basically only depends on your comparing function, not on the data type you're using.
But if you want to get fast to the item you're searching for, isn't there a better structure for doing this?
Well, if you want to, it's still, you still have some comparing. When you have some comparing and some option to order some elements in some way, binary search trees are basically optimal. In all cases, it doesn't matter how you compare them. You can comparing persons is also different, for example. So it basically doesn't matter whether you're comparing percentage or something like that. It just matters how you compare, and the structure you could always sort, or you could always do a binary search tree or something like that. Okay, and I think you said something about if you want to implement a real dictionary. Yeah, sorted dictionary, basically. If you want to implement a real actual dictionary of, for example, the Swahili language. I don't know if there's a Swahili language, but yeah, that's how you do it. You use a sorted dictionary. Okay, and sorted dictionary works with Unicode because string is Unicode, and it works with integer also. Okay, something that's worth mentioning. Here I use iDictionary. What does this mean? Well, this means that here I can put in both dictionary, the normal dictionary, and I can put in a sorted dictionary, and it will understand both of them. A sorted dictionary. Why? Well, because this just says, okay, this thing is an address in memory, and at this address we could have something. Sorted dictionary will implement its for each in one way, and our dictionary will implement for each in another way. So basically, writing iDictionary here means get whatever dictionary you want, because both dictionaries inherit iDictionary the same way as all integers, doubles, strings, etc. Inherit object. So when you use something which can be inherited by both just dictionary and sorted dictionary, it means that you can put both of them in this variable. And when you do a for each, for example, that for each will call the corresponding for each traversal for that dictionary. And the get element or get value of some key will get the corresponding, will call the corresponding method. If it's a sorted dictionary, it will call the search the binary tree method. If it's a normal dictionary, it will call the implement the hash, call the hash function and get the position. So yeah, basically the same way if you put an object here and you do a toString will be different for a double, for an integer, and for a string. Okay, not really important. What's important is you can replace both of them if you say iDictionary. But you can't use sorted dictionary specific methods, which I don't think exist. It's just the inner implementation that's different. So basically, the inner implementation of a sorted dictionary is different of that of a normal dictionary. So we could use iDictionary to store both of them because the outer methods, the methods which we see, are the same. So we can name it with this type of dictionary. Okay, as you see here, we still have a iDictionary which stores the information of a sorted dictionary. The same way which you can have an object instead of this thing. You can have an object storing the information of a sorted dictionary. But then you can't call this method because it doesn't take an object, it takes something else. Yeah, you should cast it if you want. Okay, so that's basically using inheritance. What you need to remember from here, if you need a dictionary, some sort of dictionary, in a method, and you only need to, for example, print the values in that dictionary, your method could take an iDictionary type. It isn't obligatory to say what type of dictionary. It doesn't matter. It only matters when you create it, because the compiler needs to know what kind of dictionary it should create. And then when you tell it, put it in this, this thing over here knows what methods exist in our dictionary, and it can call them. Our compiler deals with that. Okay, so that about the sorted dictionary. When you need custom keys, which will be something rare, but it could happen. It could happen. What you need to do, well, we said that our dictionary relies on object.equals and object.getHashCode. So if you create your own key, your own class, and use it as a key, you have to have these things implemented. If you want them in a sorted dictionary, what you do, well, you need iComparable, so that the sorted dictionary can order them in a binary tree. Okay, so what I already taught you is built-in types, strings, date times, floats, integers, whatever, have getHashCode and have iComparable. So you don't need to bother with that. You could change it, but it already exists if you don't want to re-implement it. Okay, so you should provide an implementation. It's not a good idea to create your class and put it in a dictionary as a key, and if it doesn't have a getHashCode, bad things can happen. Okay, so for example, we have points and we want to store something for each point. So each point will be a key in our dictionary, and that key will have something. For example, I don't know what you can store for points, but for example, each point could have not only a name, but each point could say I'm in the nth quadrant. You know, points in the coordinate system look like this. We have a coordinate system, and we have some points in it. And this thing is first quadrant, and this thing is second quadrant, third, etc. So for example, we can have points, and each point could have a string which says in which quadrant it is. Not a very good example, but it works. Okay, so if you want to implement it for a dictionary, what you do? Well, you say what equals means, And yeah, what equals means x of one point is the same as y is the same of x as at the other point, and y of the first point is the same as y of the second point. Okay, and you need the get hash code function for your point, and what this get hash code function, I'm not sure if it's the best one, but it shifts x by 16 positions left, then ORs it with x shifted 16 positions right, and then XORs it with y. That's an example of a hash code, yeah, and that's magic. And you could Google, you could say, I don't have a Chrome initialized, so you could say Google making a good hashing function, hash function. And what is a good hash function? And you have some implementation somewhere. There are studies, there are works of people which created 5 pages of how to create a good hash function statistically. Use these numbers, they're magical. For example, 33 is a very good number for hashing functions. Don't know why, somebody calculated it. So yeah, if you need to make a hashing function, you need to use the number 33 along with something else, multiply it, divide it, shift it, XOR it, don't know what. But when you use that, you have a rare chance of collisions. So whatever. Implement some hash function. This could say return 42. Yeah, the answer to life, the universe, and everything. You could say return 42. But that would mean that you would have always collisions. Yeah, you will have a list, not a hash table. You will have a hash table in which you will have one cell, which is a list. Okay. So, that's if you want a dictionary, a normal dictionary. Yes, the important thing is that you need to implement both of these. Both equals and get hash code. Because yes, yes. The colleague is right. If you have some data type, its hash code should consist of everything which it has in its variable fields, meaning that point has x and y. So both x and y should participate in our hash code. If it has x, y, z, w, and don't know what else, it should use all of them in the get hash code function, because in other cases you will get more collisions. The more things you use here, the less probability of collisions. Okay, if your hashing function is okay, you can always screw things up. That's up to you. Okay, so if you want to use a sorted dictionary, you need to implement iComparable. And how do you implement iComparable? You say what compare to means. And generally, compare to in geometry means if one is different than the other, then compare them. If the x's are the same, then compare the y's. But that's the second dimension. If the first dimension is the same as the first dimension of the other point, then compare the second dimension of the first point to the second dimension of the other point. And this thing, as we said, compare to, is already implemented for integers or doubles or floats or strings. So we can use it. It doesn't mean that you have to do this dot x minus other point dot x, because that's what compare to does, I think. Something like that. But you should always implement using the inherited function. Okay, so this is the base function for integer or whatever. Yeah, it's an integer. So this is the base thing for integer, so use that. Don't implement your own. When you use a compare to, when you implement a compare to, base that on existing compare to's. When you use equals, base that on other equals. Not like here. Not like here. Here, equals doesn't use the integer equals. This thing should say x dot equals p dot x and y dot equals p dot y, like this. X dot equals p dot x, and the same thing for y, and return that. Don't use this. It's not very good code. Okay, in the general case. Okay, so that's how you implement a dictionary with are comparable, and then you can create a dictionary with points, for example, with points as keys. Yes?
Sorry, one question. Compared to, does it have to return always -1, 0, and 1? Or it can return other...
That's why I said you should use this. Because you don't need to ask yourself that question.
Because this always returns...
Yeah, because this complies to the standards. Because today it will return -1, 0, and 1. After 5 years, someone will decide, no, compare to will return -42 and +42. For some reason which I can't think of. And that's why you use these base functions. Because if someone changes them, your application will be updated without you having to update it.
Yeah, you always have to narrow it down to...
Yeah, you always have to narrow it down to the built-in stuff. Because this thing is also built-in. But compare to isn't a sign like this, for example, and it isn't built-in. For example, you don't have a symbol for compare to. So, okay, here, this equals means the same thing as dot equals. But here, you don't have anything for compare to. And your equivalent of compare to could be minus that and get some result and normalize it to 1, for example. But that's not a good idea. Just use compare to. Just use things which you already have. Don't reinvent the wheel. Okay. Sets. What's a set? Well, a set is a multitude of things which don't repeat themselves. A set is the numbers, the natural numbers, 1, 2, 3, 4, 5, 6, etc. are a set because you don't have repeating numbers. You don't have 1 twice. For example, 1, 1, 2. That's Fibonacci, not the natural numbers. So Fibonacci is not a set, but the natural numbers are a set. And we have sets in C#. And what a set is? Well, again, it's a abstract data type, and it's present in many languages. What it should do? Well, it should contain elements which don't repeat themselves, meaning that it has to implement, the elements in it have to implement equals. And it can add elements. It can check for whether an element is contained in that set. And it could delete elements. And the best thing, union and intersect. These are things from math, basically. If you need sets, you will basically need them for math stuff or somewhere where you need to check. For example, you have a set of people which are in the C# Academy. And you have another set of people which drink a lot. And you say that, for example, the set of people which will become workers at Telerik is equal to the intersection of the people in the academy and the people who drink a lot, for example. That's my example. It's not guaranteed that it will happen like that. And the union is, what's a union? Well, a union is the people who won't get a lot of money are the people who aren't in the C# Academy, combined with the people that I don't know, can't think of. They are going to get a lot of money. I said the people that aren't going to get a lot of money, combined with the people who work for the government, for example. That's a union. Okay, so that's what set does, and it does it fast because generally it does some optimization. It's not really obligatory for you to know what it does. You just need to know that it's fast, and sets are good at adding, especially at adding at a certain position if you know where you should add, approximately where you should add. Okay, so sets again can be implemented dump with a list or array. They can be implemented with hash tables and balanced trees. Why? Well, because when you want to add an element in a set, it first has to check whether that element is present in the set. How does it check? Well, does it contain the key something? Or that value or whatever. It does. Okay, I won't add it. That's it. A balanced tree, well, search through the elements of the tree and see if a key like that exists. If it doesn't exist, add it. If it exists, don't add it. And basically that's how a set works. You have the iSet interface, and this interface is inherited by the ordered set and the hash set. So sets are either ordered or hash tables. Either a binary tree, this is a binary tree, or a hash table. And they implement it in the exact way I told you. If it exists already in the set, don't add it. If it is found in the binary tree, don't add it. If its key exists in the hash table, don't add it. That's it. Else add it when you're adding an element. When you're searching for an element, binary search here, and something else in the hash table. Searching. What?
iSet contains key, and you are saying this element is going to return an exception, or?
No, iSet is, you can't create an iSet. You can create an ordered set or a hash set and then put it into an iSet. You can consider the iSet as a remote control. You say which one it controls. You create the TV. This is the TV, and you say I will use the TV through this. That's why it's called an interface. You say I'll use the TV through this. The same thing for the iDictionary. You create a dictionary and you say I'll use it through this. I don't care what type of dictionary it is. I know that it has these functions, the same functions which are here. And when I say call me that function, it goes through the thing you've saved in it. You've said this remote control goes for this TV over here. And change channel of this remote control means call this function, because I've said that earlier. Because I've defined that thing as this. You can't create an iSet object. You can't create iSet dictionary equals new iSet. You can't do that. That's an abstract class, an interface, or whatever. You just use it as a remote control. When you don't care what you've memorized in it. You don't care if your TV set is, don't know, Fujitsu or Nokia. I don't know if Nokia make TVs. Fujitsu or Nokia. You just care that the function go to the next channel, goes to the next channel. Okay, so that's it for interfaces. The hash set, as I told you, is just in some hash table, and these things in the hash table don't have any order. So if you want to get them ordered, you don't use a hash set. If you want, however, if you want fast checks whether the element is already in the hash in the set, you use a hash set. For example, when do you use a hash set? Well, you have a set in which many elements will come in. For example, 100 elements will come in per second. Then you use a hash set. Why? Well, because it's fast. Because it can really quickly check whether that element exists in the set. Because it's a hash table and just does the hashing function and gets the result. If you use an ordered set for that, it will use a binary tree. And each time it has to check whether an element is there, it will go through the entire tree. Not the entire tree, but a logarithm of n elements of the tree. That's what it will pass through, and that's still slower than just doing the hashing function in the general case. Okay, so adding, and this thing is very fast because it checks whether the element is there very quickly. Removing the element, again fast. Count and union and intersect with, you get what it does. I already told you. Unions and intersections. This is how we use a hash set. Do we have an example? Yeah, we have an example of a sorted set. So, this is how we use I'm not sure why this guy is here. I really don't know. Yeah, I don't know why probably someone decided that hash set sounds like hell set. Whatever. Okay, so, as I said, here's my remote control. It's named like this. And it controls this guy, the hash set. And that's it. The first set, remote control, controls a hash set, which has these things in it. Another set, another remote control, controls another hash set. The second set, remote control, controls this hash set. The union of these hash sets will be an iSet. Why? Well, I will use a remote control for the TV which is produced when I call these functions. And I don't care what TV that is. I really don't care. I just care that the changing of channels or getting elements is the same. Meaning that it works. Okay, I don't care how it works inside and what it's called. I just care that I use it. Okay. And we have some method print set which says for each of the elements in the remote control, print that element. Okay. So, sorted set, what does it do? Well, by the way, union width says change this thing over here and make it equal to the union of the two things. It doesn't give you a new set. It operates on this one. Same thing with intersect width. But if you say intersection, that will give you a result, a new set, and won't operate on this one. But intersection is not a method of set, it's a method of I collection, I think. And this is specifically a method of iSet, and it's faster, generally, in the general case. Okay, so sorted set, again, an abstract data type, it does the same thing which the hash set does, but it uses a binary search tree. What it's good for? Well, getting the elements in order. If you want a set in which you want the elements in order, you use a sorted set. And you know that you won't add elements all the time. Because if you add elements all the time, this will be slower than a hash set. Not much slower, but still slower. Okay. So, elements sorted in increasing order. When you traverse the tree, when you say for each element in that set, you will get them in increasing order or decreasing order or whatever. Whatever your comparer is. Okay. So, your data type here has to implement iComparable. We already spoke about that. And how do you use sorted sets? Same way. Create mere remote control. This thing isn't obligatory. You could always say, I need a sorted set of strings, which is first set. But if you want to save up writing and you don't really care that that's a sorted set, you can use this remote control. When you see I, that means remote control. Okay, interface or remote control. The remote control is the interface for the TV. Yeah, Captain Obvious to the rescue. Okay, so what do we have here? We have a sorted set. We have some elements in that set. How do we put elements in that set? Well, we call the constructor, which uses an array. These things have constructors. You can check them out. There are different constructors. You don't have to remember them all. There is always Google. Okay, so an I set. The second set is something again with some values in it. And you say, the result, I want an I set, a remote control to the result. And the remote control will contain, for example, a new hash set. Why hash set? I don't know. This is the union and union width. I'm not sure what these guys do. Yeah, create me a hash. Yeah, this is an example that you can do union and intersection between a hash set and a normal and a sorted set. So this doesn't mean that this has to be a hash set. It could be a sorted set. You could do the intersection of a sorted set, but you could also create a new set, which is a hash set, and tell that hash set to create its union with the sorted set. That thing is possible. And you will get the result in this remote control. And you won't know whether it's a sorted set or a hash set, and you don't really care. Okay, so, and if you really want to know, well, then you just do an intersection of hash sets, if you want a hash set. If you do an intersection of sorted set, you will get sorted sets. Okay, and then you print that thing out. Let's see it live. Go to Solution Explorer, sets example. We have some hash sets and other hash sets. Display union and intersection. What does this thing do? Well, it takes one set and it takes another set and then does the union and intersection of these sets. How does it do? Well, we create a remote control, which is a new hash set. And in that hash set we say, create the union with the second set. Then create the intersection with the second set. What will we get from this? Not this. Again, I forgot to set this as a startup project. compile it again with hash sets. What happens? We create a set of Perl, Java, C#, SQL, and PHP, and a second set with Oracle, SQL, and MySQL. And what's its union? Well, the union is all of the elements, meaning these. And the intersection, well, that thing searches and does it fast, and searches through these elements in the set and says, okay, SQL is here, and all the others don't coincide, because we have SQL in this one and SQL in this one. So in the intersection will contain SQL, but the other things don't match, so we won't have them. And intersections are faster with hash sets. Why? Because you have to check whether the element exists. And when you check whether the element exists, you use a hash set because it's faster at checking. Okay, using sorted sets, you get the same result. But the sorted set is ordered. The union, when you calculate it, is ordered. Why? Well, because you made a union with the sorted set. Even though you use an I set here and some hash set and etc., you pass it a sorted set. We say display union and intersection with first set and second set, where first set and second set are sorted sets. That's why the result is a sorted set. You could try those things out and see when they're faster, see when they're slower. Okay. And that's basically it about intersection. You get the same result in the end, not this result. You get this result at the end. The same values, only that they're ordered. Okay. So, where did we get to? We saw the hash set, and basically that's everything you should know about sets and dictionaries. You will use sets relatively rarely, because except for deciding on which people go to the NLP camp and at the same time go to the C# lectures, that's things you can do with sets, and those things are fast. Or if you want to search which people have similar symptoms and diseases. For example, one person is sick of some disease and another person is sick of another disease, and you have the set of symptoms, and you say the intersection of these is these and these and these symptoms. That means that, okay, most of their symptoms are the same, which means that probably both of the diseases which they are suffering from are probably caused by the same virus. For example, that's a use case of sets. Okay, so you will most often use dictionaries, both for translating. How does Facebook work? Facebook has text files, for example, or something else, I'm not sure, or some kind of database, and in that database it's set. The Bulgarian word for like is, for example, U is vie. And when it starts translating, it checks which of these words it has, and instead of printing out you like this, it takes all of the words and puts them in the place of the English words, all of the Bulgarian words, and puts them in the place of the English words. When it doesn't have a translation for some particular word, it just uses the English word. It says, does it contain the key of this word? Does the Bulgarian dictionary contain the key of like? If it does, print out the value at that key. If it doesn't, just print out the key. That's it. That's how Facebook translates. Okay, and you can write your own translator in that way. Of course, it will translate literally, meaning that it will just get some words, but you can prioritize. You could say that this sentence means this sentence in Bulgarian, and say the priority of this is bigger than just one word, and that's how Google Translate works. Well, not exactly like that. Google Translate, you won't be able to write it, guaranteed. But that's the basis of how it works. It uses hash sets and dictionaries and binary trees and etc. Okay, so what you need to remember: dictionaries, either a hash table or a balanced search tree. Which one you use? Well, depends on what you want. If you want fast checking and fast adding and fast getting elements, you use a hash table. If you want order, you use a balanced search tree, meaning a sorted dictionary. They map keys to values. The hash function is what takes some object, some string for example, and translates it into a position, meaning a number. A hash function generally takes something, doesn't matter what, and transforms it into a number. And a good hash function transforms different things to different numbers. Not so good hash function sometimes transforms different things to the same number, but only sometimes. And a bad hash function transforms everything to 42, for example. Okay. When you have a collision, meaning that two things translate to the same number, you need some kind of collision handling. For example, chaining, putting the things in a list. I said there are other ways, but there aren't that widely used and effective. So hash tables, very fast at inserting, deleting, and finding. And the sorted dictionary is slower than the normal dictionary at these things. Not much slower, but a little slower. Okay. Sets hold group of things, and these groups have elements which are unique. Those elements don't repeat themselves. You can't have a key twice. You can't have a key twice in dictionaries also. That's why many sets are implemented as dictionaries. And these things hold groups of elements, and you can do unions and intersections with them. And those unions and intersections are fast. Generally, much faster than doing intersection on a list, for example. Okay. And they're implemented either as hash tables or as balanced trees, meaning that they're sorted or they're not sorted, but they're fast at checking. And that's basically it. So, if anyone has any questions, you can ask now or later. Yes?
We have add method to dictionaries. And how the dictionary sizes? List or like doubling sizes?
I would make a linked, a normal list. I'll repeat the question because it's probably not obvious at the recording. So, what do you do with a hash table, a dictionary, which needs to resize? If it's a hash table, if it's not a sorted dictionary, if it's a normal hash table, you need to double its size. You need to use a list. Why? Well, because your hashing function gives you a number, and that number is a position. So you can't really use a linked list. If you use a linked list, going to that position will be slow. So basically, if you're using a hash table for your dictionary, you use a list, which resizes, for example, doubles its size, or triples its size, or whatever. And if you have a binary search tree, meaning a sorted dictionary, well, then you don't have any problem with resizing. A balanced tree is actually a linked list of some things. Okay, anything else? Sets work at the same principle. If you have a hash set, it will use a list, and when it has to resize, it will double the size, and it will still use indices. And if it's an ordered set, it will use a binary tree, and there you don't have any problems with resizing. Okay, anything else?
Are dictionary and I set implement something else?
Are they implemented by? You mean is there a remote control for iDictionary and iSet at the same time? I'm not really sure. You can basically not. Yeah, they're implemented by iCollection. iCollection or something like that. But iCollection doesn't know whether it holds a dictionary, a set, an array, a list, or whatever. So if you want something specific, you need either an iSet or an iDictionary. You can't have something summing them up because they're meant to do different things, basically. You could use an iCollection and just get the elements if that's what you want to do. The iCollection implements exactly that. An array or a list or any sort of data structure which has more than one element in it. That's iCollection, and you can say for each element in the collection. If you want only that. But if you want something more specific like get me the value or something like that, you will need to be more specific at what you're using exactly. That's the idea. Okay. Any other questions? Okay, you can ask later too. Okay, finishing this recording and letting you go home. Bye-bye.